Have you ever wondered about the future of energy? Why are we still facing an energy crisis in the 21st century? As we stand here today, our world is gripped by an escalating energy crisis. With our population ballooning and our industries expanding, the demand for energy continues to soar. Yet our conventional sources of energy are a double-edged sword. Fossil fuels like coal, oil, and natural gas have powered our progress for centuries, but they're finite and rapidly depleting. Worse still, their usage churns out copious amounts of carbon dioxide, accelerating the pace of climate change. Renewable energy sources such as wind, solar, and hydro provide a cleaner alternative, but they are often intermittent and location-dependent, making them less reliable. So, we find ourselves on the precipice of a dilemma, needing a sustainable, reliable, and clean energy solution. Enter nuclear fusion, a potential game-changer in the energy sector. So, what exactly is nuclear fusion? This is the question that has led scientists and researchers on a quest for the holy grail of sustainable energy. Nuclear fusion, in its simplest form, is a process where two lighter atomic nuclei combine to form a heavier nucleus. It's the same process that powers our sun and all the other stars in the cosmos. To truly understand nuclear fusion, we need to dive into the heart of an atom. Atoms are composed of protons, neutrons, and electrons. The protons and neutrons form the nucleus, while the electrons orbit around it. During fusion, the atomic nuclei are heated to extremely high temperatures, creating a state of matter called plasma. This intense heat provides the energy needed to overcome the natural repulsion between the positively charged protons. Once they get close enough, the strong nuclear force takes over and fuses the nuclei together, releasing a tremendous amount of energy in the process. Now you might be wondering, how is this different from nuclear fission? Well, in nuclear fission, the process is almost the reverse. A heavier atomic nucleus splits into two or more smaller nuclei, accompanied by the release of energy. This is the process used in traditional nuclear power plants. However, it produces radioactive waste and carries the risk of a nuclear meltdown, making it less desirable as a long-term energy solution. Nuclear fusion, on the other hand, promises a clean and virtually limitless source of power, with minimal radioactive waste. It's like having a miniature sun right here on Earth. And the fuel for fusion? Deuterium and tritium, isotopes of hydrogen which are abundant in our oceans. Just a liter of seawater could provide as much energy as 300 liters of petrol, all thanks to fusion. But of course, achieving controlled nuclear fusion is no easy feat. It's akin to taming the sun, and that's a challenge that scientists around the world are working tirelessly to overcome. Now that we've delved into the science of nuclear fusion, let's look at how we can harness this process on Earth. How do we capture the power of the stars in a laboratory? Well, we have developed several designs for fusion reactors, each with its unique approach to controlling fusion reactions. First, we have Tokamaks, the most advanced design, which uses magnetic fields to shape and contain hot fusion plasma. This donut-shaped reactor has shown promising results in achieving high plasma temperatures and pressures, key ingredients for fusion reactions. Next, we have inertial confinement reactors. These use laser beams or ion beams to compress a small fuel pellet, creating conditions for fusion. The challenge here lies in achieving a perfect symmetry in the implosion, to prevent the fuel from escaping before fusion occurs. Lastly, let's talk about stellarators. These are similar to tokamaks, but their twisted shape provides a continuous magnetic field, making them potentially more stable for longer duration fusion reactions. These designs are our human-made stars, each with its unique approach to harnessing fusion energy. However, achieving controlled fusion on Earth is not without its challenges. What stands between us and a practically infinite source of energy? Well, it turns out, it's not as simple as flipping a switch. The road to achieving controlled fusion is paved with technical and engineering challenges. The first hurdle is containing the plasma, a hot, charged gas where fusion reactions occur. This task is like trying to hold the sun in a bottle. Traditional materials can't withstand the extreme heat, and so researchers have turned to magnetic fields for a solution, but this is easier said than done. Creating a stable magnetic field strong enough to contain plasma is a feat in itself. Then there's the question of achieving the high temperatures and pressures required for fusion. We're talking about millions of degrees, much hotter than the core of the sun. At such extreme conditions, atoms collide with such force that they fuse together, releasing energy. But heating plasma to these temperatures and maintaining them is a monumental challenge. And let's not forget about the energy balance. For fusion to be a viable energy source, the energy produced by the fusion reactions must exceed the energy used to heat the plasma. Achieving this positive net energy is another significant hurdle. Despite these challenges, progress is being made in the field of fusion research. Scientists and engineers worldwide are working tirelessly, pushing the boundaries of what's possible, inching us closer to the day when fusion energy becomes a reality. One of the most promising efforts in fusion research is the ITER project. This international endeavor is aimed at demonstrating the feasibility of fusion as a large-scale, carbon-free source of energy. ITER, which is Latin for the way, underscores the project's potential to pave the way to a new era of energy production. Situated in the south of France, the ITER project is a marvel of modern engineering and international cooperation. It brings together 35 nations, all pooling their resources and expertise to build the world's largest tokamak, a machine designed to replicate the reactions that occur at the heart of the sun and stars. The ultimate objective of this ambitious project is to generate 10 times the amount of energy it consumes. That's right, the ITER project aims to produce 500 megawatts of fusion power from just 50 megawatts of input power. This would be a monumental achievement because it would demonstrate that fusion power can be a practical, sustainable energy source. A key aspect of ITER's mission is to sustain a fusion reaction for a prolonged period. Unlike previous experiments that achieved fusion for just a few seconds or minutes, ITER aims to maintain a fusion reaction for as long as 30 minutes. This would be a significant stride towards a functioning fusion power plant, which would need to sustain a fusion reaction indefinitely. But the road to harnessing the power of the stars is not without its obstacles. The ITER project faces immense engineering and scientific challenges. From handling the extreme temperatures in the tokamak to managing the complex magnetic fields, every aspect of the project pushes the boundaries of what's technologically possible. Yet the international community remains undeterred. The ITER project is a testament to what humanity can achieve when we work together towards a common goal, and that goal is nothing less than a game changer. A clean, virtually limitless source of power that could revolutionize our energy systems and help us combat climate change. With projects like ITER, the dream of harnessing fusion energy is getting closer to reality. Why is fusion energy so important for our future? Well, let's dive into that. In our quest to combat climate change, we are in dire need of sustainable energy sources. Traditional fossil fuels like coal and oil are not only finite but also heavy contributors to greenhouse gases. This is where nuclear fusion comes in as a game changer. Nuclear fusion has the potential to provide clean and virtually limitless energy. Unlike fission-based nuclear power, which involves splitting atoms and creates radioactive waste, fusion combines light elements such as hydrogen. This process, inspired by the sun itself, results in a massive amount of energy and leaves behind only harmless helium and a neutron. No long-lived radioactive waste, no risk of a meltdown, and no contribution to global warming, but that's not all. Fusion energy not only carries the promise of drastically reducing carbon emissions but can also help us achieve energy independence. Imagine a world where we no longer have to rely on geopolitically sensitive regions for our energy needs. A world where energy is abundant, clean, and accessible to all. That's the promise of fusion energy. Now let's talk safety. One of the major concerns with fission-based nuclear power is the risk of a catastrophic accident. But with fusion, the process is inherently safe. A fusion reaction requires precise conditions of temperature, pressure, and magnetic containment. If any of these conditions are disrupted, the reaction simply stops. There's no risk of a runaway reaction, and no possibility of a Chernobyl or Fukushima-like disaster. Furthermore, the fuel for fusion comes from readily available resources. Deuterium can be extracted from seawater, and tritium can be produced from lithium, which is abundant in the Earth's crust. This means fusion energy could potentially power the world for millions of years. In the quest for clean and virtually limitless energy, nuclear fusion could be our brightest hope. But it's not just about energy production. The application of fusion technology could revolutionize other fields as well, from space propulsion to medical isotope production. This is why international collaboration in fusion research is so vital. Together, we can unlock the power of the stars and usher in a new era of sustainable energy. So, the next time you look up at the stars, remember, the same process that lights them up could one day power our world.